Hi gang, I'm going to explain how a Wimshurst machine works. For those who aren't familiar with it, a Wimshurst machine is an electrostatic machine that produces a high voltage and is often used for making sparks. But I've powered many things with it over the years, such as a Corona motor, Franklin's bell, a T-laser, a ball cyclotron, a smoke precipitator, and more. I've made it be handheld, and I've even mounted it on a bicycle. So here's how this very useful machine works. First, a little background information. Like everything else, the Wimshurst machine is made of atoms. Atoms are made of negatively charged electrons and positively charged protons. The electrons can move around, but the protons are stuck in the atom's nucleus. If you have an area with more negative charge than positive, then we say it's negatively charged. Likewise, if you have more positive charge than negative, then we say the area is positively charged. And if there's the same amount of both, then we say it's neutral. Lastly, like charges repel each other. So two negatively charged electrons will move apart. And two positively charged atoms would also move apart, if they were free to move. And unlike charges attract each other. So this negative electron is attracted to this positively charged atom. Now on with how the Wimshurst machine works. For the Wimshurst machine to start, there needs to be an unbalanced charge somewhere on either of the disks. The machine has two disks made of an insulating material, like plastic. The disks are rotated by turning a crank. That crank turns two large pulleys. From one pulley, a belt goes up to a smaller pulley that's attached to a disk and turns the disk. From the other pulley, another belt also goes up to another smaller pulley that's attached to the other disk. But that belt is twisted. That twist makes that disk turn in the opposite direction. Each disk has metal strips on them called sectors. As we said, for the Wimshurst machines to start working, there has to be an excess positive charge or an excess negative charge on any one of the sectors. If the air isn't too humid, then there usually is this random unbalanced charge somewhere. So let's say we have an excess negative charge on this sector. If we have a negative charge on that sector, then that will influence the way the charges are arranged on the sector across from it on the other disk. Since like charges repel, and since electrons can move, the negative charges on that sector are repelled to the other face of that sector, leaving the closer face positively charged, and the outside face negatively charged. That influencing of charge on another sector is called induction, or more precisely in this case, electrostatic induction. Electrostatic simply means the charges are static. They aren't moving around like they could around an electric circuit. But then our sector with the excess negative charge is moved away, and the other sector goes back to normal. However, now our charged sector influences the next one, and so on. Eventually our charged sector gets to a point where the sector on the other side is being touched by a neutralizer. The neutralizer is this metal bar here. That bar has metal brushes on either end, one touching a sector here, and the other touching a sector at the other end of that disk. There's also another neutralizer bar facing the other disk. Notice that they're both mounted diagonally, touching opposite ends of the disks. But more importantly, notice that since the metal brushes on either end of the metal bars are touching both sectors, that means those sectors are electrically connected to each other. Charge can flow between them, if it wants to. What's happened is that the neutralizer bar and the far sector have become metal extensions of this sector. And so the repulsion from our original negatively charged sector continues its influence over that whole extended sector. The repelled negative charges now have further to be repelled, and so they go all the way down to the far sector. Notice that because those negative charges went to that far sector, that sector is now negatively charged overall. And since those negative charges left this sector, it's now positively charged overall. As the disk continues to turn, our now positively charged sector eventually faces another sector on the other disk that's touching the other neutralizer. Since it is touching a neutralizer, and that neutralizer is also touching a far sector, we see the same thing we saw with the other neutralizer and sectors on the other side. They all act as one electrically conductive object. Remember, only the negative charges, the electrons, can move. So the positively charged sector on the other disk attracts negative charge all the way from the far sector, making one sector negatively charged and the other sector positively charged. And notice we're back to the same side that had the negatively charged sector that started it all. That means that unless something happens to change everything, we now have negatively charged sectors moving from the neutralizer brush here, positively charged sectors moving away from the neutralizer brush here, and on the other side of the disk we have positively charged sectors moving away from this brush, and negatively charged sectors moving away from this brush. On the left and right sides of the Wimshurst machine, we have what are called collectors. Their job is to collect the charge. Notice that from what we just described, only positively charged sectors are moving towards this collector, and only negatively charged sectors are moving toward this collector. These collectors are U-shaped. They have sets of sharp metal points on them facing each disk, called combs. Using the negative side as our example, the negative charges on the sectors repel negative charges from the sharp points, leaving them positively charged. Those negative electrons will go to the rest of the circuit, but we'll talk about that later. There's an electric field between the charges on the sector and the charges on the sharp points, and we can visualize that field by drawing lines between the charges. Since the charges are crowded together at the sharp point, the lines are closer together, meaning that the electric field is stronger there. That strong electric field attracts electrons from the neutral atoms in the air. It also attracts electrons from the sectors, leaving the sector neutral overall again, as it rotates away from the collector. The next negatively charged sector that comes along will repel those electrons out to the rest of the circuit, and so on. Meanwhile, a similar thing is happening at the other collector, except that since the sectors there are positive, negative electrons are flowing from the sharp points to the sectors, neutralizing the sectors. And so we have negative electrons being collected at this collector, and negative electrons being removed from this collector. The next parts are these two things, called Leyden jars, which is just the old name for a particular shape of capacitor. A capacitor is an object that has one electrically conductive plate facing another electrically conductive plate, but with an insulating material in between them. You can accumulate opposite charges on each plate, and these charges will attract each other. But because the insulator is in the way, the charges won't cross over and neutralize. In this way, you can build up a voltage across the two plates. Leyden jars are the same thing, except that the plates are cylindrical in shape. You have an inner metal cylinder that you make contact with from the inside, and that goes to a collector. Then there's a jar-shaped insulator around that, and then an outer metal cylinder that you can make contact with from the outside. In a Wimshurst machine, we have two of these, though one bigger one would do just as well. Their outer plates are connected together with a wire, which is normally hidden underneath. If you were to draw a schematic for these two Leyden jars, then it would look like this. Two capacitors connected in series, and both going back to a collector. And so what we're doing is collecting negative charge on this side and putting it on the inner cylinder of one Leyden jar, making that cylinder negatively charged. Meanwhile, we're collecting negative charge from the inner cylinder of the other Leyden jar, leaving that one positively charged. Since the outer cylinders are so close to the inner cylinders, negative charge is repelled from the one with the negative inner cylinder and attracted to the one with the positive inner cylinder. The Leyden jars become charged. But there's still one more capacitor here, albeit a very poor one. That's the spark gap. As we said, the collectors are connected to the inner cylinders of the Leyden jars, but they're also connected to the ends of the spark gap. That gap is where the spark occurs. That spark gap is a capacitor, with the two plates being round metal balls, and the insulator between them being air. We can add it to our schematic as another capacitor that's in parallel with the two Leyden jars. And just as with the inner cylinders of the Leyden jars, negative charge goes from one collector to one ball, making that ball negative. And negative charge is removed from the other ball and goes to the other collector, making that ball positive. As with any capacitor, there's an electric field between the two sides. But unlike with the collector, there are no sharp points here, and so the charges have more room to spread out. That means the electric field doesn't get as strong as quickly, and more charge can accumulate without crossing sides. And eventually the electric field in the spark gap gets strong enough to break down the air, and we get a rush of a lot of charge across it. That charge comes from both the spark gap capacitor and the Leyden jar capacitors. That's the spark. The spark gap has become a short circuit for the capacitors. Immediately after that, the two sides of the Leyden jar and spark gap circuit are neutral again, and we start over, collecting charge from the Wimshurst machine's disks. There's just one more thing to mention. We started this whole thing by saying there has to be a charge on a sector somewhere for all this to start. But what if there isn't? In that case, you can induce a charge. The easiest way to do it is with the triboelectric effect. Basically, I rub a cotton cloth against a plastic rod. That charges the rod negatively. When I bring the rod near to, but not touching, a sector, where the sector on the other side is touching a neutralizer brush, that will cause the necessary induction to charge that sector through the neutralizer bar, just like we talked about. That gets it all going. And recall that I've used this Wimshurst machine for many demonstrations. There are links to the videos of all those demos in the video description. And that's how a Wimshurst machine works. Well, thanks for watching. See my YouTube channel for more informative videos like this. You can support these videos either through Patreon or through a one-time donation. And if you like these videos, don't forget to subscribe, give a thumbs up, share with your social media, or leave a question or comment below. See you soon!